Second presenter today is Gregory Parenteau. Parenteau came to us here as a transfer student about years ago. In the first year, I kind of wondered whether or not he would mesh with the rest of the group. But I realized to my delight very quickly that he became very comfortable with his peers, looking like he's been here all along, which was very, very nice to see. Within his first year here, I also quickly realized that he likes to tinker with things. His way of learning difficult materials such as electronics or microcomputers is to just mess with them, you know? So needless to say, when he chose this current senior thesis, I was quite happy because I knew that he would mess with it long enough to get it working. So his talk is entitled Wireless Mouse Design Based on Electronic Systems. It's a great pleasure to welcome Gregory Parenteau.
Thank you, Dr. Cornley. As he said, my name is Greg Parenteau, and I'll be presenting on the wireless mouse design based on an energy coil system. First off, I'd like to start off with a little overview. What I'm going to be talking about today. I'm going to start with my introduction, move into what gave me this motivation behind this thesis. I'll give you a little bit of background about it, the methods I went through, and of course, the development process and the struggles I had there. And finally, I'll go into the results and the future work I'd like to do in this field. We'll start off with the backbone of this presentation, mutual inductance. So as you'll see here, mutual inductance is a magnetic flux that's created in one inductive coil, and it couples into a nearby coil. So as you'll see here, the current from I1 is going to come into L1, the coil, induce this coil, which in turn is going to couple with L2 right here, this coil, and it's going to cause a voltage to come out of this. Now this is the basis for my project because what I need to do is create a wireless power supply. I need to get voltage from this coil system to my mouse in order for it to work. A little bit further into mutual inductance, show you a little equation right here. So what this equation is saying is there's a time varying current, which is shown right here, that allows for this induction to happen. Moving a little further, got a little bit of a picture presentation here. As you'll see, it shows the changing magnetic field, which produces an electric current in the loop. As you'll see, the magnet right here is going into this. It's causing current to come out. Same thing for here, and this one is the last one. I didn't do that one, but it involves a switch. Moving on from here, my motivation. Why did I do this? So initially, it turned out to be a really dumb thing, but I started off, I was working on my computer one day, and my mouse died. Battery was dead. Oh no, what do I do? No batteries in my cabinet. I'm kind of out of luck there, so had to go to the store and get batteries. So it made me think, I wonder if there's an easier way to power this mouse without actually using a battery or a wire directly connected to my computer. So I started doing research on it, and I found these two designs which weren't already working with a mouse, but it was a similar basis. They were able to power light bulbs, and of course they were both done by MIT. So figure 1 here shows their initial design, which featured a coil that could transmit power through this large distance. But one of the downfalls was the coil is pretty big, if you see here. It's about 2 feet. Can't exactly put that on my desk. As you'll see in this one right here, they condensed it a little bit, but by doing that, they lost the distance. The distance significantly decreased, but the coils also decreased, so it's a little bit more feasible. So it made me think to myself, what could I do to make smaller coils for my mouse, but maybe not get this great distance? So I started looking into it. I set some goals for myself. So first one, of course, I needed to design a wireless mouse. I needed to make it so that this mouse would run with no battery and no support from a USB port. In order to do this, the mouse had to be powered from an electromagnetic induction in a coil system. But in doing this, the mouse itself spit out some requirements that it was asking of me. The mouse needed 1.5 volts and 100 milliamps in order for it to function, and that's where I started getting into some of my problems, was getting these outputs from my coil. Next, I'm going to jump into the architecture. So these are some of my high-level requirements for the mouse, of course, or for the coil. mouse next. So first off, of course, the coil has to be compatible. It has to work with the mouse. Another thing, I wanted to work with other devices in the future, maybe expand, so this isn't such a one-dimensional project. The coil also has to produce power. Doesn't want to produce too much power where it overloads the mouse, but enough so it works. It's got to hold the power distributed, and it needs to have a good range. So the power needs to be distributed through, as I said before, that short distance, so it's actually wirelessly inducing the coil. So I was thinking maybe 1 to 3 inches seems ideal to start with. It's a good spot. Same thing goes for the mouse. So the mouse, high-level requirements, needs to receive power from the coil, needs to store that power, and it needs to have a max so it can't overpower the mouse and shut it off. In doing this, I started to encounter a lot of problems. So this led me through a very long and extensive development process. So it was good in the sense that I got to go through a full development cycle of a product, but it took a lot of debugging and fixing. So I'm going to talk a little bit now about the development process. So first off, I had to develop a test system that could induce current in a small coil. I'm going to call that System 1. I'm going to refer to this a couple more times through the presentation. With System 1, I had to modify it so I could reach the first requirement of the mouse, which is 1.5 volts. With that, I'm going to call it System 2, another thing I'll refer to a couple more times through this presentation. With System 2, I had to reach the final requirement, which was 100 milliamps from this coil. And once that's done, along with the 1.5 volts, I'd like to call that my final system. Once I have my final system, I want to verify that it supports the human factors that I'm going to talk in the next slide and the requirements, so I could integrate it and test it in everyday use. So the next part, go with it. Laptop froze. Yeah, we could. Oh, we're good. Yeah, I had it. All right, we're back up. So human factors. First one, it's not as big. I wasn't within, or the design was so small that it didn't really affect the exposure. That's not really the problem here. The problem was, as you'll see here, milliamps. When I'm working with milliamps, I have to be very careful. If you touch it, if it touches you, if you're working with these live circuits, that's a bad idea. You always need to make sure the power's off. You're not touching any wires while the power's on, because if you do, well, we'll say this area, shoot low, is the area I was working in, cause extreme pain, respiratory arrests, muscle contractions, and last but not least, death is possible. And that's on the lower side of things. That was the beginning. When I got to the 100 milliamps, it put me in the really bad range where death is likely. Need to be careful. Made me feel great every day. But anyways, so once I had this, I worked around the human factors, make sure I could do this. What makes this product better than the MIT designs? What makes it usable in today's society? Well, I think I'm going to compare them a little bit. MIT, it's got those big coils. I can't put that on a desk. I don't want to put it in my room. But they have the good distance, so that's their plus side. On top of that, they were working with light bulbs. I don't need to put light bulbs in my house that way. Mine, on the other hand, it uses small coils. I only get a few inches, but it's still compact. I could put it in my backpack and take it with me to school. I could carry it with me if, say, I'm powering a phone when I'm hiking. And it's also for the mouse, but as you'll see in later slides, that I would like to change that and work with other things. And last but not least, size does matter in this case. Finally, I'm going to get to the circuit design, the bread and butter. So this is my initial design. In order to test this, I used an LED just to make sure that I could actually induce the coil. When I did it, the LED lit up. Perfect. It allowed for me to then say, I'm ready to test this. Let's see what I'm getting out of it. Am I ready to meet those requirements of the mouse? This leads me to my initial circuit data. Not very good. I need 1.5 volts. I'm only getting 20 millivolts. I need 100 milliamps. I'm not even getting 1. What could I do to better this? how could I take that voltage and bring it up almost or over a full volt? Leads me to the debugging phase of this design. First off, I had to put in a voltage rectifier. What a voltage rectifier does is it takes the AC input coming from the coil and turns it to DC. Not only does that, this is a full wave rectifier, so what it does is it takes the normal sine wave you're getting from the AC and it rectifies it so you're getting all amplification. So this design here, because there's 3 stages going through it, you get triple the voltage you were initially putting into it. Want to see how this works out in my data section? Sure enough, it worked. I was getting the voltage I needed, but as you'll see in red here, the current's still not there. That's the next problem I have to tackle. How could I do this? I need current gain. Well, what simpler way than add a current gain amplifier? So what this does is it takes this voltage in right here and it creates a current, or this voltage in right here creates a current coming through this leg right here. That will go through this transistor right here, which you could pick based off what you want, and it'll give you your amplified current out of this leg right here. After I did that, I ran some tests to make sure that it actually did work the way I expected it to, and sure enough, we're getting my 100 milliamps of current, still getting my voltage. Nice, I think I'm ready to plug in the mouse, wouldn't you say? Plug in the mouse, next problem happens. I'm clipping at a constant of 0.78 volts. That's not what I need. I need double that. I need that 1.5 volts in order for this mouse to work. This clipping was actually happening because the mouse was regulating the voltage itself, so it couldn't cause harm. It didn't want to overload itself, so it would clip the voltage. In order to fix this, I put in a voltage regulator. I decided to regulate the voltage myself to try and trick this mouse into thinking that it was the one regulating this voltage. This voltage regulator here is perfect because it includes a negative feedback loop, which is the main part behind tricking the mouse into thinking it is the one regulating the voltage. Once I did that, I have my final circuit data. The mouse is able to get the 1.23 volts, 100 milliamps. It works. Let's try and power it up. This brings me to my first video. I don't know if there's any sound. Oh.
Receiving about 1 volt and around 100 milliamps.
So just a minute.
Running by wireless induction.
Perfect. My mouse turned on. That's great and all, but what am I going to do with that? I have a mouse that works. Wouldn't you say I should plug it into a computer? Let's see if I could get some actual application out of this. Which brings me to my next slide, and next video, which I messed up a little bit, but you'll see when it shows it.
And there's nothing on the screen. So what we're going to do is go and turn the mouse on, getting 1 volt in. The mouse is turned on, and now we're going to try and activate something on the screen with the mouse.
As you'll see here, I didn't show my hand with the mouse, so next slide will show the hand to make sure I'm not faking this by any means.
Can you go back and stop it and show me the different parts that you've been talking about there?
That's actually on the breadboard design. It's, yeah, I could try and find it. I don't know what's happening right now.
So is all of that going to go inside the mouse sooner or later?
Yeah, so right here, this side right here is your first coil. This is the first design I showed you. It comes in this coil, induces it, comes through this coil. Right here, this big long thing right here, that's my voltage rectifier. From there, it comes into my current gain amplifier, which is right here. This is a little transistor. And that flows down into my final voltage regulator, which is meant to trick the mouse into thinking that it's actually regulating the voltage. That's connected to the power supplies.
Are you going for something like a coil sitting over here on the side?
Yes. Yeah, I would like to have the coil, you could put it behind the computer and the mouse is able to work in front of it. For some reason this video started going crazy.
The wireless mouse. The mouse is on. There's nothing on the screen. So what we're going to do is go and turn the mouse on, getting 1 volt in. The mouse is turned on, and now we're going to try and activate something on the screen with the mouse.
You can see the mouse moving right there. I'm going to go down and activate Google Chrome.
Chrome here.
So the mouse works. Allows me to click. Yeah.
It's running. We're going
They show
to the voltage,
the amps I'm getting.
the current,
Getting my 100 amps.
milliamps of current,
Echo.
and we're going to go back to voltage. Make sure it's still on. Mouse is running. Google Chrome.
Had to throw that in at the end. Just natural thing to make a fool of myself. From that, I mean, I just saw you couldn't see my hand moving the mouse. Didn't want any suspicion. So it brings me to my final circuit application, a video where you could actually see the mouse moving on the screen and my hand moving that mouse.
Make sure there's power going to the mouse.
You see the power going through right there. Mouse lit up.
Moving the mouse on the screen. We're going to try and activate Google Chrome.
And there it is.
As you can see, mouse working.
The only thing I noticed with the mouse that's different than like an actual mouse application is it lags a little bit on the screen. I'm sure I could fix that somehow. I haven't really looked into it. I just tried this last week, but it works. Mouse works on the screen. My final application, I could try and condense this. It leads me to my future work, what I would like to do to make this an actual product, something I could use. I would like to achieve a further separation of the coils, maybe get that 1 foot distance between the coils so, as Dr. Free said, you could put the coil behind the computer and move the mouse around without having any problems. Another thing I'd like to try is apply this to different DC devices. You could power phones off of it, maybe a fan, maybe a clock. It would be nice to try this and make sure it's just not that one-dimensional product. It's something that could actually work in other applications. And finally, you saw that big clunky breadboard. I'd like to put this all on a PC board so it's nice and portable. I don't have to carry around a breadboard with me everywhere. If you don't know what a PC board is, it's a little board that acts as a breadboard, and you could actually solder each of those components into it, and it'll actually condense the circuit for you. That's my presentation. I'd like to thank Dr. Cornley for his help, Dr. Masco for her help, and the entire engineering department for their help. Daniel Burley helped me a bunch, and just everybody involved. They supported us through this. Had a lot of good opportunities to try this out and use the materials to their full extent that we have in the labs. Any questions?
When you showed the video there, there were wires coming out of the mouse.
Yeah, that's
Those were something else.
Yeah, so the secondary coil is connected to all those circuits. So what's actually happening is there's a separate coil on one half of the breadboard, another on the other half, and they're not connected by any means. But I need to keep, it's too hard to solder them all right now and try and fix it. So if something's wrong, I'd have to desolder everything to fix the problems, and it was a lot easier to just put it in the breadboard where you could just interchange parts and move stuff around. So that's, as I said in the future part, I want to condense it to a PC board, which would allow me to have 2 separate coils that are completely wireless. I mean, on the breadboard it's wireless, it just doesn't look that way because it looks like they're connected when they're actually not.
I guess I'm still a little bit confused. So is one of the coils going to actually be in the mouse?
Yes.
So when you're moving it around,
Yep.
it moves around with the mouse?
Yeah, that's the next problem, is trying to get that coil condensed enough so it could be inside the mouse.
More questions for Greg? Pretty quiet class.
I know.
Very good.
Thank you.